Thank you. Good morning. So it's my pleasure to talk a little bit about something called the Exascale Computing Project. So there are two key words in there out of the four, right? So what is exascale? It's not exaflops, right? So what does that mean? Perhaps I'll give you some insight of how we define it. And then project, why is this a project instead of a program? Well, first of all, how many of you have previously heard about the Exascale Computing Project? A show of hands? Oh, so yeah, you have heard of it. I wonder, what do you think comes to mind first? We're going to spend a lot of money and buy lots of hardware? But maybe we'll do something about software or applications. And of course, the answer is all of the above. Now, what we are attempting to do is to address the whole ecosystem. Applications, as I will, I hope, demonstrate, are extremely important. But then they rely on a software stack, and so you also have to have that. And if you don't have hardware to run on that's fairly well suited to the kinds of applications that require exascale, then you still have a problem, and then you have to deploy the systems and operate them. And this project, I'll say right away, is not directly buying any hardware other than little test beds, and it's not going to operate anything, because we want to generate exascale systems that are part of vendors' roadmap. They're regular products, not demonstrators, not one of a kind, things that anybody else will be able to buy as well in whatever size works for them. So that's an extremely important aspect of how we're trying to address it. So why is it a project? Well, it's a collaborative effort between two parts of the Department of Energy. It's a little bit weird, but there's a part called now the NNSA, the National Nuclear Security Administration, and then the Office of Science of the Department of Energy. And since 2007, we have been looking at what is exascale, why is it important, as you well know. And then, luckily for us, a little bit over a year ago, President Obama issued an executive order, National Strategic Computing Initiative, that emphasized the importance of HPC to the nation, and explicitly said that we should accelerate the delivery of exascale systems and integrating hardware and software capability, and measuring exascale as a ratio of petascale systems. So when you see 50 to 100 times, that's because you can think of, well, there are some 10 petaflop systems, and so if you have 100 times that, that would be 1,000. If you have 20 petaflop systems, and there are a couple, obviously a Sequoia and Titan, then 20 times 50, I used to be a mathematician, it's also 1,000. So we're getting away from talking about flops. What we care about is that you get delivered performance on real applications. So the 50 to 100 is for real complex applications that can't even be done today. And that's how we measure exascale, deliberately getting away from the flops. And so our work encompasses application systems, software, hardware technologies and architectures, and also workforce development, because you need people with the right expertise and interests. So within the National Strategic Computing Initiative, the Exascale Computing Project arises because DOE, Department of Energy, was designated as a lead agency along with the National Science Foundation and the Department of Defense to work on exascale. And so we're doing a joint program, and we also talk about capable exascale because, again, we want to emphasize it's exascale systems that have a software base that can be used by many applications fairly easily. Obviously, it will seldom, if ever, be trivial, but it should be easy enough. And so our role is this capable exascale system development and delivery. In the NSCI, there are also deployment agencies, as you know, NASA, FBI, NIH, and so on. And we'll be working with them more on the application side, of course. So the word project. Projects have a start and an end. And so we have currently a 10-year project to address the issues that I mentioned. And it's led by a number of the DOE laboratories. There are 6 core laboratories, 3 from the Office of Science, Argonne, Berkeley, and Oak Ridge, 3 from the NNSA side, Los Alamos, Livermore, and Sandia. And those are the core laboratories. And so the leadership team for this project involves people from those 6 laboratories. So I'm the project director. My deputy project director is Stephen Lee from Los Alamos, for example. So we at the laboratories are doing this. Obviously, the funding comes from headquarters, but we lead the project. But DOE has 17 national laboratories, and we anticipate that at least 16, and probably all 17, will have a role in what? Well, perhaps in developing some piece of the software stack or in developing one of the applications. So there's 6 core laboratories, but then the additional ones will also be involved. And, of course, as always, we work with industry and academia very closely. Now, I've been mentioning that we don't buy and will not be buying any computers other than test beds. Well, so who will buy them? Well, the facilities in DOE, both Office of Science and NNSA, that always buy the biggest systems, so which tends to be those 6 laboratories that are the core laboratories. And every few years they're due for a new set of very high-end systems, typically every 4 years. And there's a 2-year offset, so you'll see Los Alamos and Sandia get a system. Their next one is due in 2020, and whereas the Coral collaboration, which is Argonne, Livermore, and Oak Ridge, are they have not yet gotten their 2018 machines, but the next one after that, 18 plus 4 being 22, will be roughly around 2022. So very closely with the facilities, because they're the ones that will be buying the systems, and so they need to be regular production systems as they would normally buy, but hopefully with the help of this project, there'll be much higher performance, have a good software stack, and most important, a big set of important applications ready to do scientific and engineering discovery. So our project goals are, if you look around the bottom of these boxes, foster application development, software stack, so ease of use, 2 diverse architectures, and that's a very important part of our approach as well, because I don't think anybody knows what the winners are in terms of architectures, and architectures evolve, and also competition is healthy, and so we want to promote a healthy vendor community at the very highest end, and so you can't just pick one system. So there are many reasons to have 2 diverse architectures. And then we hope to be designing the software stack, helping vendors design hardware and develop applications that are of interest to industry as well as academia and the government. And so we always are looking for generality, because we also, because of the NSCI, see part of our responsibility as helping the U.S. remain very competitive in HPC. Similar things to what very appropriately the European Commission is trying to do for Europe. So applications, of course, is where the real payoff comes. And I learned a long time ago that when I was able to, say, get a grant to get, perhaps at the time, the world's fastest machine for science, and I'd go tell my scientific colleagues, we're going to have this system installed, often they were not happy, because they said, but my budget hasn't changed, and how can I hire people to then learn how to use this system and develop my applications for it? So one of the things that I really like about this project is we're investing very heavily in applications. That's so that you have the applications, but they each have to identify a specific challenge problem that can't be done today, that matters, that somebody cares about it, and should be feasible to address with Exascale. But we're going to not only provide additional funding to do that, we're going to hold their feet to the fire on several things that normally application teams are not required to do. Software engineering practices. Now this will be good also for human resources development, because most graduate schools in science don't even spell software engineering, much less teach anything about it. But yet, most applications involve teams, big teams, usually in DOE, distributed across different locations, academia and different labs. You have to have software engineering. So that's part of what the funding will require. And because co-design is so important and we want to have, in the end, a really usable set of systems, they have to, the applications folks, tell us their requirements in terms of software tools, algorithms, configurations, and work with other parts of the projects, the software development part for the software stack, the hardware development that I'll mention, where we're working very closely with industry to develop better node and system designs for our kinds of applications, scientific and engineering applications. Provide the requirements, and then when those other parts of the project say, okay, here's our response to meeting your requirement, they have to try it. They can't just sniff it and say, I don't like it, and I'll have my graduate student do it over the weekend. So that's extra effort, but it's really important to work closely. And so we envision that some of the software developments for, say, software tools, mathematical libraries, will be some of the time embedded in the application teams, because that's how collaboration gets done. You're elbow to elbow and addressing projects jointly. They'll have milestones, so we'll require frequent milestones for applications and all the other parts. Some of them will be joint milestones. So to meet the milestone, you'll have to have the software tool, in this example, and the application that needs that tool demonstrate that they have met that particular goal that's represented in the milestone. So that's a lot of the effort in what we call the application development part of the project. We also are establishing co-design centers for commonly used methods such as the ones here, adaptive mesh refinement, particle and cell, for example. And we're investing some in developer training programs. Some are already underway, and we'll be developing others so that we have the right workforce. Obviously, that won't solve the workforce problem, but it'll address part of it. And since I've been emphasizing applications today, we're officially announcing, the first set of 22 applications. In addition to, I'll say so I don't forget it, there are 3 NNSA applications that are already underway. But these 22 were selected from a... so just a quick reminder for those of you who may remember that in June of 2015, Department of Energy and then NSF and NIH sent out a request for information, basically saying, is anybody interested in developing exascale applications? If so, write a couple of page white paper. And so DOE got 109 such white papers, and NSF and NIH got another 130 or so. So there were over 200 applications that said, we need exascale to solve this interesting problem. So that was the initial pool, and it got winnowed down to, finally, we asked for 30 full proposals for applications, and as of today, we can announce that we've selected 22 of them. So the $39.8 million in the first round, that's the first year funding of the first round of applications. That is not the total funding, it's just first year. And they're split into 15 that are fully funded, and then 7 that we call seed because we want to get them started, but we'll be ramping them up in a phased way. So there is a public announcement, a press release, and in fact, I think HPC Wire already has something out, right, Rich? So let me give you just a whirlwind tour. The reason I have these slides on all the 22 applications because these slides will be put on the website for HPC Forum, so you can see them at your leisure. I will not go over by 30 minutes. I'll stick to my time. I assume that's the correct time. But I wanted to give you a glimpse of the breadth of the applications that we're addressing. And remember, each one has identified what we call a challenge problem that they expect to be able to solve once we give them the access to the hardware and software. So climate, nuclear energy, wind energy, chemical sciences, combustion, materials science, nuclear physics, nuclear materials, accelerator physics. So there are, among others, lots of data issues. Different kinds of material science, say protein structure and dynamics, fusion, advanced manufacturing, additive manufacturing, strangely enough, can be an exascale problem. Cosmology, very basic science, and geoscience, carbon capture in this particular case, seismic, more carbon capture, and chemical science, and even a seed project on urban science. Again, that's lots of data, very different kinds of data. So the V for variety for data, metagenomics, astrophysics, and the power grid, which managing the power grid of the United States can be an exascale problem. There's of course a strong time dependency, a time to solution. It doesn't do you any good to find out how to manage things one day too late. I mentioned that the National Nuclear Security Administration, of course, also has applications, and there are 3 applications that are described in general terms here. Done at Los Alamos, Livermore, and Sandia. So we already have 25 that are being ramped up. We want to do more, and we will do more. And we're supposed to work with other agencies. Well, the first other agency we're working closely together with is the National Cancer Institute, or NIH, for which NCI is a part. And this is something that's we've had collaborations with them for several years already. They've been, some of their researchers have had access to our biggest systems by putting in proposals and being in granted time. And so now we will be doing one of the projects on this topic, which is, of course, a great one. So projects have to be measured. You have to know, well, when did you meet your goals, and what are the goals? So achieving what we're calling capable exascale computing, we mean that supporting applications that solve science problems 50 times faster or more complex than today's 20 petaflop systems. Now, to achieve the 50x, maybe it'll take 2 exaflops. Doesn't matter. What we want is that additional capability. We're still sticking with power envelope, a target of 20 megawatts per system, maximum 30. And it needs to stay up long enough that people will use it. So we're aiming for, for the user to notice a fault no more often than every 6 or 7 days. Now, it doesn't mean that there are no faults of any kind on the entire system for 6 or 7 days. But for the average user, even using a large fraction of the system, that should be the experience. And, over the last several generations, starting in the mid-90s when the systems got bigger, all those additional parts, people thought, well, it's going to crash all the time. And the hardware has not tended to do that after initial settling in period. Software eventually settles down. And so that's what we're seeing with systems that have, 100,000 cores, nodes, and many more cores than that. So resilience. I already mentioned part of our success is we have to have 2 diverse architectures. that meet the other criteria. Has to have a software stack that meets the needs of a broad spectrum of applications. We're not doing this just for the DOE national laboratories and the applications that are identified today. And so it has to be a holistic project. We are using co-design, integration, and making a lot of emphasis on those things. And we think that's the only way that we'll come up with capable exascale, by having the applications, the software developers, the hardware developers, and the people who will have the facilities that operate them, all four of them working together. So amazingly, we've structured the project as having 4 focus areas called application development, software technology, hardware technology, and exascale systems. And so I've talked a fair amount about the applications. Let me say a little bit about the software. So we've designed this is at this point a conceptual software stack, and we're in the process of evaluating 55 proposals for different parts of the software stack. And we, in the next couple of weeks, we'll be selecting approximately 35 to fill in all these parts. Most of them, you can see, are very familiar. You always have mathematical libraries, you have frameworks, programming models, tools, and so on. Up at the top, we put visualization and data analysis above the applications in co-design. And then along the sides, you notice resilience and workflows, because those, we believe, impact everything. You know, you don't just do resilience in one place. You do it at the hardware level, and then you do it at the very low level, the kernels, and then on up. And so the responsibility for resilience in software is everywhere. You can't just say, do it here. And then workflows, because we are seeing and have selected some applications that will involve real-time transfer of data from, say, accelerators, or it could be sequencing machines, that then require some preliminary analysis and maybe filtering, but then need very, very soon a big computer to do the analysis so that you get the results that you need. And so the exascale system will be part of a broader ecosystem managed by workflows, and that will impact many different parts of the overall ecosystem. So in hardware technologies, we are using an approach that's been used in the past fairly successfully over the last 20 years or so. So this one we're calling Path Forward. And so we issued a draft RFP in April, and then a formal RFP on June 16th to the vendor community, the companies that design and build hardware and entire systems, as well as components. And so the Path Forward RFP resulted in 14 proposals from 10 different companies. And we recently selected a subset of those companies with which we'll start negotiating specific parts of their proposals. So what do the proposals have to be? We want them to address either no design or system design for exascale, or both, and address problems that, issues such as partially the resilience, certainly the energy consumption, and the programmability, ability to get real performance out of the hardware. And in a 3-year period, come up with something that hopefully can be bid as part of a vendor product for the next set of systems, which would be the ones that the facilities will be putting out an RFP for in 2019 and would be installed in 2022. So it's not just think up something really neat, but think up something really neat that meets our needs and that has a good probability of becoming part of a vendor's product offering at the end of roughly 3 years, so that it can be bid as a result of the RFP issued in 2019. So again, not a one-of-a-kind system, not just demonstrate a good idea, but something that can be integrated into an offering by a vendor's product roadmap, not a potential thing. So that's the approach, and we did get a lot of interesting proposals, and as usual, we wish we had about 50% more money available because there are that many really good proposals. And the proposals, by design, we asked them to do work packages so that it wasn't just a monolithic proposals. Some companies had 20 work packages. That way we can pick the parts that we feel fit best our needs. So now, if you fund all that, which we very soon will be doing, we're starting the negotiations with the vendors, then you need to have a way of determining whether those designs are likely to be any good. And so we have an effort. So this is people and software tools that we call design space evaluation. And so we'll have expertise from around the labs and academia to measure ideas. And initially it'll be through simulation, but then as hardware starts to happen, then it'll be based on actual systems or preliminary systems. So this 10-year project, as we now have formulated it, we think of it as being in several phases. This is a slight rewording, just some points. So the 3 years, we're funding applications, software stack, co-design, hardware, and that's the path forward stuff, the vendor node. So we've got 3 years to get a better handle on what needs to be done, but with milestones all along the way, not just tell us 3 years from now what you've learned. And then in 2019, all the things that learned in those first 3 years will feed into parts of the request for proposals for what would be the first exascale systems at the DOE National Laboratories. So a big impact on that. We don't issue the RFP, we the project. It's the facilities, because it needs to be the usual process. Now, what we will do as part of this project is supplement money for the facilities. So one quick example would be, over the last few years, these very high-end systems have tended to cost $150 million each. We anticipate the first exascale systems might cost more than that, maybe $250, maybe $300 million each. So as part of this project's funding, we're planning to have, when the time comes, 2021, 2022, a piggy bank in which we can supplement what the base funding of the facilities have for buying the system. Similarly, for site preparation, they might need a bit more square feet, a bit more cooling. They have a budget for that, but we'll supplement it. And then maybe most importantly, for these build contracts of these new systems, we've been issuing, along with a build contract, a non-recurring engineering contract to improve the initial build proposal. And so we, in this project, are planning to supplement the amount of money that can go towards non-recurring engineering for those first systems. So you can think of it in one scenario is it's a transition of something we funded with Path Forward. It really looks good. It was bid by a vendor as one of the features, but it maybe needs a little bit more work, and so that'd be an NRE, non-recurring engineering contract, to that vendor who's doing the build system. And so that's one of the ways that we're working with the facilities. Now, the facilities also have requirements for software to manage the systems, and so they're participating in coming up with requirements for the software stack and managing the system. So then, by the time the facilities have decided what they're buying, these two diverse architectures, then the applications people and the software stack people will have a better idea of what their target initial exascale systems will be, and they will start modifying their algorithms and implementations as appropriate and making it ready for production, because again, these are not supposed to be research software items of interest, but something that can be used in earnest for real applications at the top scales. So that's what we mean by productized in software technologies. Then when the systems get delivered, in my experience, they never work exactly as you thought they would, and so then it'd be good to have a couple of years where you deal with the real software delivered by the vendor, the real hardware behavior, and then the applications themselves. When you first run them at scale with the real data that you want to solve the problem, you may, it's happened once or twice, find out that there's something not quite right. But at that time, we're cruising, I would imagine. So it's a young project, but we've solicited and selected proposals for applications. We're about to co-design centers very soon, selection. Software technology activities, again, we're in the final phases of evaluating all those proposals, and we've selected hardware technology R&D. So all those things are in flight. So applications, software, hardware, and we expect the initial awards of the software part to be this fiscal year. For the hardware, it'll be early in the next fiscal year, as is indicated here. So that gives you a glimpse, and the clock just turned to 0, I think. So thank you very much.
Questions? Doug?
So let me get my notes here. I thought I saw something on there that said something about co-design centers for commonly used methods, and adaptive mesh refinement was one of the items.
Correct.
Is there an opportunity to collaborate with private industry on some of these activities? Because I know there's more than one company out there working on adaptive meshing.
Correct. Yeah, something I should have mentioned. Thank you for that question. In what we call the software technology part of the project, we are planning to do an RFP that's actually aimed at independent software vendors, which would be, one example of which would be maybe companies that do adaptive mesh refinement. And although the co-design centers are part of what we call the application development part of the project, the boundary there for co-design centers is, between software and applications is very thin. So bottom line is we are intending to issue an RFP to work with commercial software vendors in some areas, and that will probably come the second half of FY17. So not in the far distant future, but in a few months.
Some of the key players may not be software vendors.
So could you? So I'm not sure what you meant. I thought you were talking.
This industry is spending a lot of money on solution adaptive meshing.
Right.
So people like Lockheed Martin and Boeing are not in the market for selling software, but they're very much in the market for looking for solution adaptive.
Oh, sorry, I misunderstood you. Yeah, so that absolutely, we'd be very happy to work with them. And one way that would provide an entry to it is we're establishing an industry council. So this would be it'll be fairly large, 25 to 30 people. In fact, I'm fortunate to have Susie Titchener and David Martin who are here working with us part-time in our project to put together the industry council. And this is end-user industry, not computer vendor industry. And so from that, we expect to have guidance of, are we developing things that are useful for industry? It also provides an opportunity for identifying collaborations. And so, yes, I think that we definitely could work with industry. We often do already, not in the Exascale project, but at the national laboratories. So in terms of, if your thought was, these industries have a lot of expertise and a lot of need, and so they could both provide some expertise to us, but also help us develop the right things for them, which is what we want to do. Thank you. Yeah.
Thanks for clarifying.
Yeah.
Any other questions?
So you talked about workforce development. How much of the resources are going to be shared outside? How much, what are you focusing on? In other words, there's a lot of other efforts going on. So who all are you working with, and how are you leveraging that?
Well, yeah, you're right, and so obviously we will be working with other agencies as well. What we're doing right now, the very first steps is we brought into this project a 2-week training program that was established 4 years ago, which is called the Argonne Extreme Scale Computing Training Program. And so that is open to actually the world. So each year we admit 60 to 70 people who already have a lot of expertise, and they've done something non-trivial at a pretty high scale, and in those 2 weeks we cover even more advanced things for them. So those people from industry, people from national laboratories, and so it's by no means restricted to DOE or DOE national labs. So that's only on average 65 a year, but over 4 years, it's a few hundred. And I'm pleased to say many of the graduate students have then gotten very good positions, or the postdocs have gotten staff positions either in industry, some of the oil companies, for example, or national laboratories. So that's the one specific thing we're doing already, because we already had that going. I started it 4 years ago with DOE Office of Science research funds, and now because workforce development is so important, we've transitioned it to be a small part of this project. So we envision doing more things like that, doing short courses on software engineering, for example, because I mentioned there are gaps there, and certainly working with NSF and other agencies. There's a report that's about to be issued in final form that in part deals with that Lois McInnes is writing, and so I've interacted with her on that aspect a bit. So we can't do very much for the global need or the national need, but we do want to do our part. Does that answer your question?
I have a question, Paul.
Yes, Paul.
So exascale sort of implies an emphasis to some extent on flops. And yet, a very important part of usable systems is the interconnect technology. And so, can you discuss how that subject is being worked?
Sure. Yes, I, having been associated with very large blue gene systems, I know that the interconnect technology really matters. In fact, going back 40 years or so. So the way we're approaching it is, I mentioned that the Path Forward RFP asks for node designs and system designs. So when you have a system design, you care about the interconnect. So we do want better interconnect. And so there are targeted requests for better interconnects as part of Path Forward. And then of course part of the requirements come from applications. Some applications it doesn't matter. For some it's crucial, and so that's why I mentioned the blue gene, because for certain kinds of, say, CFD applications, people who moved from a different system to the blue gene were astounded that the global operations didn't take any time all of a sudden, instead of being 50% of the time. I'll say on a personal level, I'm disappointed that we actually had much better interconnect topologies and implementations, say 20 years ago than we do now. But money matters, and so in order to save money, we don't have offerings that are quite as good, in my opinion. I like determinism, for example. So we are addressing it through, making sure that we describe the requirements that need different kinds of interconnects, and funding companies to come up with better ones.
Any other questions?
Hi, Paul. This is really an NSCI question, but you might have a comment on it. In the NSCI executive order, there was some mention of NIST is playing some role in performance characterization, but I never see them on any slides, so I'm wondering, is that real or not, or how does that factor into what's going on with the ECP?
So as to whether it's real or not, I really can't comment on that. What I will say is, I mentioned what we have as a project, and so that has specific rules associated with it. The Exascale Computing Project, even though we've been using the name for something like 8 or 9 months, it was only in July 28th, I think, that we got the official DOE stamp that we are an official project. So for two reasons, I haven't devoted much time talking to the other agencies associated with an SCI. One of them was we were not yet a project, but the other is I and all my colleagues have been busy doing the planning, issuing the RFPs, evaluating the proposal. So the real answer is I need to, over the next few months, start talking more often and more closely with NSF. We are already talking to DOD in various ways, and places like NIST, because they are part of it, and we do care about those standards. It just hasn't happened yet. I do know people at NIST, and so that's not an issue at all. But thanks for bringing that up. It's DOE, I think, because we really got started in the late part of the last decade and looking at exascale, that we're already moving pretty well, and some of the other agencies, the NSCI is only a year old, so maybe they're not quite as spun up as we are.
Well, thank you.
Thanks.